atrapalhar a conversa e nada, deixar os microfones fechados, câmeras fechadas. Qualquer coisa, vocês podem falar pelo chat, ou pelo e-mail, ou pelo Instagram. Estamos em todas as redes sociais. Qualquer coisa, vocês podem me falar comigo, já que a maioria já faz isso. Qualquer problema, a gente vai falar, e se estiver atrapalhando, infelizmente, a gente vai ter que retirar, porque para não ficar inviável o controle disso aqui, certo? No mais, acho que é isso, e só João Vitor dar o ok para a gente começar.
Professor Sean, just one thing. We are going live on YouTube on your lecture. So if you want to share it with anyone you want, feel free to do it.
Okay, there's too much of me on YouTube already, so I'll just stick to talking to you folks.
Oh, okay.
You're allowed to put it on YouTube.
Okay, thanks. Okay, so, well, it's now my great honor to introduce our last speaker in the week of Physics 2020. Of course, I wouldn't need to do that since you all have been sharing our excitement over his presence here today. You all knew he was going to come. Some of you didn't believe us until now. But yeah, it's great to have him here. But we're going to follow the protocol, and I'm going to make his introduction to you, okay? So Professor Sean Carroll, he's an internationally recognized theoretical physicist, a best-selling author of articles and books, both in the technical and non-technical level, and a well-recognized science communicator. He obtained his PhD in astronomy from the University of Harvard in 1993 with his thesis called The Cosmological Consequences of Topological and Geometric Phenomena in Field Theories. After that, he was a postdoctoral researcher both in MIT and at the University of Chicago, becoming an assistant professor there in 1999. In 2006, he moved to California Institute of Technology, Caltech, where he remains until the present day as a research professor. Last year, he also became an external professor at the Santa Fe Institute. His research spans a wide variety of subjects, some of which are space-time symmetries, dark energy, dark matter, and dark forces, the origin of the universe and the arrow of time, and the foundations of quantum mechanics. Some of his publications include the books From Eternity to Here, The Quest for the Ultimate Theory of Time, The Particle at the End of the Universe, How the Search for the Higgs Boson Lead Us to the Edge of the New World, and more recently, Something Deeply Hidden, Quantum Worlds and the Emergency of Spacetime. As a communicator of science, Professor Sean Carroll is known for his participations in many documentaries, TV programs, newscasts, as well as his social media and YouTube channel. I'm particularly a great fan of his new project in YouTube, The Biggest Ideas in the Universe. Well, there's a lot of more other things I could tell you about our speaker, but I need to let him speak. So now with you, Professor Sean Carroll.
Okay, thank you very much, Lucas. Thanks, everyone, for inviting me over here. I'm sharing my screen. Hopefully you see one image at a time. There's a cat in a box. If you're not seeing the right thing, please let me know, and I'll try to fix it. But it's a great pleasure to talk to an audience like this, especially students. And I think it's an interesting time to be talking about this subject, even though it's a very old subject, right? Quantum mechanics. Quantum mechanics became a mature field in the 1920s. And even though we've learned an enormous amount about the universe since then, especially quantum field theory and particle physics, fundamental nature of quantum mechanics remains a little bit mysterious to us. And so much so that my predecessor at Caltech has a famous quote here. I'm sure you've heard it before. Here's Richard Feynman, who says that, "I think I can safely say that nobody understands quantum mechanics." He was drawing a distinction between quantum mechanics and general relativity. Relativity, Einstein's brainchild, has a reputation of being very difficult to understand, but really it's not. You know, I wrote a textbook. You're all welcome to buy my textbook in general relativity. It's a very understandable theory as long as you put the effort into understanding the symbols and the mathematics. Whereas quantum mechanics is not even well defined. We don't even know what the final statement of the theory is. So that's a much worse situation. But it wouldn't all by itself be bad, because progress in science is driven by not understanding things, right? We don't understand something, then we try to improve the understanding. The problem with quantum mechanics is not that we don't understand it, but that we're kind of not trying to understand it. This is the weird thing that we have since the 1920s, that we know we don't understand quantum mechanics, and rather than making it a high priority target, make all the most prestigious, highly paid professorships in people who are trying to understand quantum mechanics, we claim we don't even want to understand quantum mechanics. As a field, physicists say, shut up and calculate. Don't worry about all these details about quantum mechanics. So I don't know how familiar you are with Aesop's fables. These are a bunch of stories that are supposed to teach lessons about life. And one of the famous fables is the fox and the grapes. The fox sees a bunch of grapes on a tree. They look very juicy and yummy and sweet. And the fox says, I would like those grapes, jumps up to get the grapes, but can't reach them. So eventually, after not being able to reach them, the fox says, you know what? I never wanted those grapes anyway. They were probably sour, okay? So in case it's not perfectly clear, in the terms of this parable, the fox represents physicists and the grapes represent trying to understand quantum mechanics. We tried very hard in the 20s and 30s to understand quantum mechanics. It didn't work. And so now we tell ourselves it was never important anyway. But that's a bit of a lie. We're not being very honest. Personally, I think that there is nothing more important in physics than trying to truly understand quantum mechanics. So for those of you who are not experts in quantum mechanics, let me give you the brief review of how we got here in the first place. And there's different ways of getting here. I'm not going to be historically accurate, but one of the important realizations was that atoms, as we understand them, didn't quite make sense before quantum mechanics. So you've all seen this picture of an atom, this little cartoon with the nucleus at the center, electrons orbiting around. This was put together by Ernest Rutherford and his collaborators in the early years of the 20th century. And they say that the atom looks like a little solar system, right, with the electrons kind of looking like planets. But this can't work. And the reason why it can't work is, you know, if you have an electron or any other charged particle and you move it up and down or in a circle, the electron has an electric field pointing toward it. And if you move it, the electric field shifts. And if you move it up and down over and over again, there's this shifting of the electric field that vibrates off to infinity. And we call that an electromagnetic wave, aka light, right? Radiation, electromagnetic radiation. So what should really happen in the Rutherford model is that the electron should be giving off light all the time as it's spinning around in that orbit. Now you might say, well, what about planets in the solar system? Why don't they give off light? Well, they give off gravitational waves, but gravity is much, much weaker. You can calculate how quickly the electron in the orbit of an atom should lose all of its energy and spiral right into the nucleus. And the answer is something like 10 to the minus 11 seconds. In other words, according to the Rutherford model of the atom, all matter should be drastically unstable. The chair you're sitting on, the earth beneath our feet, you yourself should collapse into a point in less than 1/100th of a billionth of a second. So something is obviously wrong. And people thought a lot about what could be wrong. They made up all sorts of rules. Niels Bohr especially was a leader in this field. And eventually they hit on an extremely radical idea, which is that the electron doesn't spiral into the center of the nucleus because the electron is not a particle at all. You should think of the electron as a wave, what we call the wave function of the electron, which is kind of a boring name for something that is very, very important in physics. So if you say that the electron is spread out, that it is a wave-like thing that has different values, the wave function of the electron is a complex number at every point in space, okay? And this little diagram here shows you different shapes that the electron wave function can have. And the point of these shapes is, this is very important for understanding the name quantum mechanics, okay? Quantum mechanics is not called quantum because reality comes in discrete chunks. It's exactly the opposite of that. In quantum mechanics, reality is a wave, okay? It's the smoothest thing it could be. It's not like it's made of particles anymore. But when you have a wave and you impose boundary conditions, like on the edges of a string in a violin or a guitar, and you pluck it, you only get certain frequencies. That's where the discreteness comes from in quantum mechanics. It's not intrinsic discreteness, it's waves in the presence of boundary conditions. So in an atom, The wave, that is the electron's wave function, has a boundary condition that it goes to 0 at infinity. And these different shapes you're seeing here, the different orbitals that the electrons can be in, are the different discrete shapes that you can use to build up any shape the electron might have. And then you think you've understood, you've explained why electrons don't decay, why they do not spiral into the center, because the wave has a minimum size that it can possibly obtain without increasing in energy, right? If you try to squeeze the electron into an even smaller region of space, its energy would go up. So these are the allowed orbitals for an electron. That explains why matter is stable. And then even better than that, here's Erwin Schrödinger, who came up with an equation for the wave function of the electron, the Schrödinger equation. As you all know as young physicists, once you have an equation, that's the best, because now you can ask questions about the evolution of the wave function, how different wave functions interact with each other, why the shape of the wave function is the way it is, and so on. And I know that there's different sort of levels of expertise in the audience, so I'm not going to go into details, but here is the equation. And the equation is basically on the left-hand side. If you say that this Greek letter psi is the wave function, h is something called the Hamiltonian. It basically asks the question, what is the energy of this wave function? And usually, wave functions are going to be superpositions. They're going to be combinations of different energies. And then on the right-hand side, it's the rate at which the wave function is changing over time. Okay, so basically the Schrödinger equation just says the more energy is in the wave function, the faster it changes over time. That's all you need to know. So by itself, this is a very beautiful, wonderful, pristine theory. You have a function, the wave function, a complex valued creature. You have an equation that explains how it evolves with respect to time. This is just like physics has always been, right? Ever since Isaac Newton said F equals ma. You have a system and you have an equation for how it evolves in time. That was for Maxwell's equations, for electromagnetism. It's true for Einstein, true for equation as well. So what's so hard to say about the thing that electrons are really waves, not particles. Electron, you observe it, you look at it in an experiment, and what you see is something like this. This is a little chunk of radioactive substance in a cloud chamber. Okay, so this little, I think it's radium, little chunk is giving off particles as it is radioactive. Okay, and what the Schrödinger equation says, every emission of a particle should be a wave-like thing that spreads out equally in all directions. But what you see in this picture are discrete straight lines. Okay, you see trajectories of individual particle-like things. So this is the fundamental puzzle of quantum mechanics, that when we talk about what the electron is when we're not looking at it, we say it's a wave. But when we observe it, when we measure it, it looks like a particle. So which one is it really, okay? And this is a puzzle. People came up with a way to sort of get around this puzzle that was never very satisfying. They said that somehow the wave function of the electron knows when you look at it, and when you do, it collapses, okay? So on the left-hand side of this diagram, this is an example of what the wave function might look like when you're not looking at it. The wave function of an electron in an atom or something like that. You see it's kind of all spread out. And then the new rule that people invented, Max Born especially, was another German physicist. He said, what the wave function is a way of calculating the probability of seeing the electron at any given position. Where the wave function is large, there's a lot of probability. Where the wave function is small, there's only very little probability. And after you measure it, the wave function collapses. It goes from being all spread out to being localized near one location, something that looks like a particle, okay? So in other words, the fundamental weirdness of quantum mechanics is that things like electrons behave differently when you are and are not looking at them. And as a result, those of you who have taken quantum mechanics in a class, you know that there are two different sets of rules for how quantum systems behave. When nobody is looking at the system, everything seems nice. Everything seems just like classical mechanics. There's a state of the system called the wave function. We know what that is. We know what wave functions are and how they interact. There's an equation governing how the wave function changes over time, namely the Schrödinger equation. And ordinary sets of physical theories would stop there. But quantum mechanics keeps going with a whole bunch of new rules for what happens when you look at a system. The wave function collapses to some value, and you can't predict exactly what that value is going to be. It's randomly chosen with a probability distribution given by the wave function squared, okay? So this is what has come to be called the Copenhagen interpretation of quantum mechanics, or you might just say the textbook interpretation of quantum mechanics, because this is what we teach our students. Different professional physicists will argue over what we really should call the Copenhagen interpretation, but this is certainly what we teach our students. This is what is in the textbooks. This is what, since the 1930s, we've decided to say quantum mechanics is all about. So just to drive this home, this sort of distinction between not looking at something and looking at something, let's turn to our favorite thought experiment, which is Schrödinger's cat, okay? Now, I actually have changed the Schrödinger's cat thought experiment a little bit. Erwin Schrödinger came up with this thought experiment because he actually was upset about the Copenhagen interpretation of quantum mechanics. People like Schrödinger and Einstein never went along with it. Despite being very influential, successful physicists, they lost the marketing battle a little bit. And so the Schrödinger cat thought experiment was not designed to make people go, wow, quantum mechanics is really weird. It was designed to make people go, surely that can't be right. We need to do better than this. So in the original version of the thought experiment, there's some quantum event, like a radioactive source, like we already saw, and a detector that if it observes that source going off, opens up a box of gas that goes into a bigger box, and then there's a cat in the box. And in the original version of the experiment, the gas was cyanide, it was poison, and it would kill the cat, okay? And so Schrödinger's daughter once said, I think my father just didn't like cats. So I personally have changed the gas into sleeping gas. There's no reason to kill the cat. But the same physical point remains, that Schrödinger is saying, if you believe quantum mechanics, something really weird is happening inside this box before you open it, okay? Because quantum mechanics is very clear that you say that there's a probability that something happens or something, but that probability is only manifested when you observe something. Before you observe something, it's not a probability. All of the different options are there. That's one of the crucial features of quantum mechanics. The wave function of a system, like the wave function of a cat, allows for a superposition of different possible observational outcomes. So what quantum mechanics says is, it's not true that the cat is either awake or asleep, you just don't know. What's true is the cat is in a superposition of both being awake and being asleep until you open the box and observe it. So classically, this is supposed to illustrate the difference between classical mechanics and quantum mechanics. And what I've done is I've invented a notation for the purposes of this talk where classical things are in square brackets and quantum things are in parentheses. So classically, you might say to yourself, well, if I haven't opened the box yet, the cat is either awake or it's asleep. I don't know which one. There's some probability I'll get either answer when I open the box. But quantum mechanics is saying something different. It's saying that the cat is literally in a superposition of both until you open the box and observe it. And again, Schrödinger's point is supposed to be you can't really believe that that's actually true, right? But just to drive it home, let's go through what happens in the Copenhagen interpretation of quantum mechanics. A crucial feature of the Copenhagen interpretation is that the observer, in this case it's a picture of Niels Bohr, the observer is treated classically, okay? The observer is not treated as a quantum system themselves. Even though observers are made of atoms and atoms are quantum mechanical, somehow observers are treated classically. So here we're treating the cat, we're not counting the cat as an observer. The cat is quantum mechanical, the observer, Niels Bohr, is classical. So you say before the box is open, the cat is in a superposition and the observer does not yet know what's in the box. After the observer opens the box, the wave function of the cat collapses, and either the cat is awake and the observer saw it awake with some probability, or the cat was asleep and the observer saw it asleep with some probability. So this is clearly unacceptable. as a fundamental theory of nature, okay? This is, I'm not, you know, as you know as well as I do, this is what we teach our students. This is what we pretend to be right, but it's clearly not good enough. And let me just highlight 2 reasons why it's not good enough, okay? One reason is what I call the reality problem. And this does not get a lot of attention, but I think it's very important. I talked about the wave function, right? And we all have solved Schrodinger's equation for square wells or harmonic oscillators or whatever. And you know the wave function is the fundamental thing that you analyze. It's the equation that you solve, okay? So what is the wave function? What does it really, truly represent? Is the wave function supposed to be exactly the real world? Like if you were classical mechanics, if you said there were a bunch of particles, if you're Isaac Newton, you say there's a bunch of particles, they have positions and they have velocities, and that's the real world. That's what I'm describing, okay? It's a mathematical model of the world. When you talk about the quantum wave function, is it also a mathematical model of the world, or is it only part of the mathematical model of the world? So there are people who believe in what are called hidden variable theories of quantum mechanics, where you have the wave function and also extra things like positions of particles all together in the quantum description. There's another set of people who say that the wave function isn't the real world at all. It has nothing to do with the real world. The wave function is just a way of characterizing our ignorance of the real world, and we use it as an algorithm for making predictions, but you shouldn't attach any reality to it, okay? So the point is not that one of these is right and one of these is wrong. The point is that we don't know. 90 years after we invented this theory, we're still struggling to say what the wave function is, and that's a little bit embarrassing. The more famous and well-known problem is called the measurement problem, okay? I mean, I was trying to bite my tongue when I gave you that description of the Copenhagen interpretation, but clearly the act of measuring or observing plays a crucial role, right? The rules are different when you are observing a system or when you are not. So what counts as a measurement? In the Schrodinger's cat experiment, we imagine to ourselves that a human being opening the box counts as a measurement, but the cat does not count as a measurement. So who says that? What about a really smart cat? What about a person who opened the box but didn't look inside? What about a video camera, right? How quickly do measurements happen? When exactly do they happen? None of these questions are answered by the Copenhagen interpretation. They're just assumed that we know it well enough, okay? That you don't need to worry too much about exactly what happens, okay? And this makes people think that maybe human consciousness is somehow involved. We don't know. But one way or the other, it's something where we haven't given you the answer to this very, very important question. So these kinds of questions, the reality problem, the measurement problem, these are what are tackled by the subject known as the foundations of quantum mechanics. And like I said, modern physicists mostly ignore the foundations of quantum mechanics, and I think that's a bad idea. So here is my favorite answer to these questions. It was given by Hugh Everett in 1957. Hugh Everett was just a graduate student at the time. You know, many of the best ideas in physics are invented by very, very young people, so keep that in mind. And he gives a very simple answer. He says, look, what is the wave function? What is reality? They're the same thing. The wave function is an exact representation of the real world. There's nothing more to it. There's nothing less to it. And what happens when you make a measurement? He says a measurement is nothing special. A measurement is just an ordinary physical interaction. The only thing the wave function ever does is evolve according to the Schrodinger equation. We all think that wave functions evolve according to the Schrodinger equation sometimes. Everett says wave functions evolve according to the Schrodinger equation all the time. They never collapse. There's nothing random or unpredictable about it. So in other words, here are Everett's rules for quantum mechanics. There's only one set of rules. Systems are described by wave functions, and they always obey the Schrodinger equation, right? So that sounds much simpler, much easier, much more compact, the Everett interpretation versus the Copenhagen interpretation. But we already know why it's difficult to believe, because we said as a matter of the data, as a matter of empirical observation, that when you open the box in Schrodinger's cat, or when you look at an electron, or you look at a decaying nucleus or something like that, you don't see wave functions. So if the whole world's just a wave function evolving with time, why do we see particles rather than waves when we look at electrons? That's the fundamental challenge for Everettian quantum mechanics. And the answer, according to Everett, has to do with entanglement. Entanglement is this feature of quantum mechanics that Albert Einstein and his collaborators emphasized back in 1935. The famous EPR paper, Einstein, Podolsky, and Rosen, really pushed entanglement as a central feature of quantum mechanics. And I will illustrate it just for fun in terms of the Higgs boson, okay? So a Higgs boson is the particle that we really love. I wrote a book about it that Lucas kindly mentioned, the particle at the end of the universe. We discovered it in 2012. It's the only known particle that has zero spin, the only known fundamental particle that we know about. So every elementary particle has a certain amount of spin, and it can be a positive number, a negative number, or it can be zero. The electron, for example, has spin 1/2. That's in units of Planck's constant. The Higgs boson has spin 0, okay? And spin is conserved when particles decay and so forth. But the Higgs boson with 0 spin can decay into two particles with non-zero spin, okay? Let's say an electron and a positron, the anti-electron. So when that happens, in order for spin to be conserved, it better be the case that if the electron is spinning one way, the positron had better be spinning the other way, okay? They have to be spinning in opposite directions from each other. Now, because it's quantum mechanics, you don't know whether the electron is spinning one way or the other way. But because of conservation of angular momentum, you know that whatever way the electron's spinning, the positron is spinning the other way, okay? So this leads to what is called quantum entanglement. So it's not that the Higgs decays into an electron spinning up and a positron spinning down, or vice versa. It decays into a superposition. There's one part of the superposition where the electron is up and the positron is down, and another where the electron is down and the positron is up. So you don't know. If you ask, what is the spin of the electron? You don't know. Maybe it's up, maybe it's down if you were to measure it. But what you know is whatever measurement outcome you get, the other particle will have the opposite. And that's true, and this is what bugged Einstein. That's true even if you take these two particles and separate them but by light years away and then measure them. Okay, you measure one and instantly the other one knows. And so Einstein thought that somehow it must have been predetermined what spin answer you were going to get. We now know that's not true. Bell's theorem and a whole bunch of other quantum results that I won't get into. But what I want to emphasize here is the entanglement between these two particles. So just to emphasize it a lot, I'm going to say the same thing again in different words. One way of saying it is there are not separate wave functions for every particle in the universe. If you were doing classical mechanics, you said a particle has a position and a velocity. Well, every particle has its own position and its own velocity. They're not related to other particles. So you might guess in quantum mechanics that two particles each have their own wave function. Like maybe electron has this wave function, a superposition of up and down, and maybe the positron has this other wave function, also superposition of up and down. And what I'm telling you is no. And what I'm telling you right now is not the Everett interpretation. This is just quantum mechanics. This is just the rules of quantum theory that literally everyone agrees on. There's only one wave function, the wave function for the universe, and it is allowing you to have these entangled superpositions where the two particles are related to each other in a specific way, okay? And that is the feature of quantum mechanics that Everett is going to use to make sense of what we see when we observe electrons. So let's, rather than talking about electrons, let's talk about Schrodinger's cat once again. So remember, Everett is saying everything is quantum mechanical. There's no classical observers. So there's only parentheses here. There's no square brackets. I'm putting the observer, who is Hugh Everett in this case, into parentheses. So the observer has their own wave function, right? The observer is not purely classical. This is what Everett says. You can't just say that you're special because you're a big macroscopic being. You're made of quantum things just like everything else, okay? And what happens when you open the box and look at the cat? What happens is whatever physics says happens, whatever the Schrodinger equation predicts. And we know what the Schrodinger equation predicts. So here's the initial state where the cat is in a superposition of awake and asleep. The observer hasn't yet looked at the cat, but then you open the box, that's called the measurement, and you interact through the laws of physics. You look at the cat, you pet it, whatever you want to do, and what happens is you and the cat evolve into an entangled superposition, okay? So there's now part of the wave function which says the cat was awake and you saw it awake. There's another part of the wave function which says the cat is asleep and you saw it asleep. Okay. Again, everyone agrees that this is the prediction of the Schrodinger equation. The disagreement is whether we should believe this prediction of the Schrodinger equation. And it's clear why you might be tempted to not believe that, because you might think naively that if you were to open the box and this is what actually happened, you would feel as if you were in a superposition, right? That's what the equation says. There's part of you that saw the cat awake and part of you that saw the cat asleep. But nobody in human history has ever felt like they were in a quantum superposition. No one has ever thought, yes, part of me saw the cat awake and part of me saw the cat asleep. Part of me saw the electron go in this way and another part saw it go that way or spin up and spin down or whatever. In all of our experience as human beings, we've only ever seen definite measurement outcomes. So how in the world can you believe this crazy scheme that Everett suggests? Well, the answer is a phenomenon called decoherence. And decoherence is just the same story again, but it's taking really, really seriously the idea that there is only one wave function for the entire universe, okay? So I say there's only one wave function, and I talk about the cat and the observer. Well, what about everything else in the universe? So if we're strictly being careful, we should include everything else. And what I mean by that is we should include the box, we should include the air in the room, both in the box and outside the room. We should include all the photons that are in the room, okay? So we group them together, call them the environment. And so here's a picture of the entire quantum state of the universe, where the little picture of grass leaves represents the entirety of everything other than me and the cat, okay? And we call that the environment. And what happens is the cat is a big macroscopic thing, okay? So the cat is either awake or asleep. We said that was the superposition that it was in, but we were cheating a little bit. We left out an important component because the environment, which includes, for example, the photons and the air molecules in the box with the cat, the environment interacts differently with the cat if the cat is awake versus being asleep. So that causes entanglement. So even before the observer opens the box, the environment becomes entangled with the cat. So you might have a situation where if the cat were awake, a certain photon would hit the cat and be absorbed, whereas if the cat were asleep, that photon would just pass right on by. So what decoherence is the process by which a quantum system becomes entangled with the environment. And you can run through the numbers. Again, it's all just physics. It's all just equations. There's nothing mystical going on here. And what you find is that decoherence happens all the time, and it happens very, very rapidly. It's an extraordinarily effective, efficient, rapid process, okay? So long before you open the box, the cat has become entangled with the environment. And only then do you open the box and you become entangled with both. Why do we care? What difference does it make, right? Why are we interested in that? So let me draw the picture again. So here's the cat, the environment, and the observer. The crucial move, the brilliant genius thing that Everett figured out was these two parts of the wave function, one where the cat's awake, the environment monitored the cat being awake, and the observer saw the cat being awake, and the other one where the cat was asleep, etc. Once the environment becomes entangled with the cat, these two parts of the wave function don't interact with each other anymore. It's a technical thing, which we could go into the equations for, but what you would say is the quantum state corresponding to the environment with the cat awake versus the cat asleep are orthogonal to each other. They're perpendicular, okay? So what that means is there's no more quantum interference, no more interaction at all between what happens in the part of the wave function where the cat's awake and the part of the wave function where the cat's asleep. Again, everyone agrees with this. This is not the controversial part, okay? So whatever it says is we can therefore treat these two different parts of the wave function as if they are separate worlds. The reason why you have never experienced being in a superposition where you saw the cat awake and you saw the cat asleep is because you never have been. What happens when you open the box is not that you evolve into a superposition, but that you evolve into two different people. living in two different worlds, one in which a world where the cat was awake, the other one of which a world where the cat was asleep, okay? This is why the Everett interpretation is sometimes called the many worlds interpretation of quantum mechanics, because every time a small quantum system becomes entangled with the environment and decoherence happens, the world branches into multiple copies where different things happen. But the important thing I want you to really appreciate, if you, from nothing else, from what I'm talking about here today, Everett does not start by positing a large number of worlds. He starts by positing that there's a wave function that always obeys the Schrodinger equation. That's it. The worlds come out. The worlds were always there. Hilbert space is the name we give to the set of all possible wave functions. And in anyone's version of quantum mechanics, Hilbert space is big enough to describe many, many, many parallel copies of the world. And Everett just says, and they come to pass. And again, it's not anything. It's not every single world comes to pass. The Schrodinger equation brings certain worlds into existence. And this is what happens. It's the prediction of the equation that we all know and love. What it's asking you to believe is that that's okay, right? It's a more therapeutic move than a physics move. Like, don't be bothered by the fact that there are multiple copies of people who descended from your past self. So there are sort of good and bad worries to have about the many worlds interpretation. Let me tell you some of the bad worries, the misconceptions. One is that there's just too many worlds, right? Like it's extravagant. It's not simple. It's not, sorry, I'm hearing someone talking now. Someone's microphone turned on. The idea that there are too many universes in the wave function, in the Everett interpretation, is just a restatement of the fact that the space of all wave functions is bothersomely big. But that's true, like I said, in everyone's interpretation of quantum mechanics. If you believe that quantum mechanics can describe an electron in a superposition of spin up and spin down, then you should be able to believe that quantum mechanics can describe you as being in a superposition of I saw the electron spin up and I saw the electron spin down. And if you believe that, you should be able to believe that the universe could be in a superposition of the electron was spin up and the electron was spin down. The math is the same for all of those different things. Everett does not put in a bunch of universes. He points out that they were always there in the quantum formalism. The other misconception is that you can't test it, right? Like Everett is predicting all of these different worlds and you can't observe them, so it's not really science. But that's, again, a complete misunderstanding of the physics. It's not just bad philosophy of science, it's bad science, because what you do with physical theories, if you want to test them, you don't test every single prediction they make, you test the predictions that are testable, right? And the Everett interpretation is simply the statement that there are quantum wave functions and they only ever evolve according to the Schrodinger equation. So the question is, are those axioms testable? And the answer is certainly yes. There are alternatives in which they're not true. And in fact, the tests are going on right now. The Everett interpretation is completely falsifiable. We know of experiments that would falsify it right away if they came out a certain way. I don't think it will be falsified, but it could be. Finally, a misconception is that it costs energy to make all these universes, and energy conservation is somehow being violated. That's not really true. Energy conservation is more preserved in the Everett interpretation than in any other interpretation of quantum mechanics. It's just that the view of energy is different from inside the universe than the God's eye view of the entire wave function of the universe. So when the universes are created, they're not equal in stature. You know, there's a weight or a thickness to the universe given by the wave function squared, okay? And as the branching happens, the universes get thinner and thinner. You don't notice from the inside, but the total contribution to the energy of the universe is smaller per branch of the wave function as the universe keeps branching. And this is something where, again, the mathematics, the equations are completely 100% crystal clear. There's no real ambiguity about this. Nevertheless, there are people who don't believe it, and so therefore they presented alternatives, which is good. We should have alternatives to test against. So like I said, there are people who believe there are additional variables in the universe over and above the wave function, okay? hidden variables, you might call them. Sometimes these are called pilot wave theories of quantum mechanics, like Bohmian mechanics. And there are also spontaneous collapse models. There are models where wave functions really do collapse, and it's really unpredictable when they're going to collapse, and they really do so in a non-deterministic way. Both many worlds and Bohmian mechanics are secretly deterministic, but there are truly non-deterministic versions of quantum mechanics. So what I want to do to close the talk is talk a little bit about sort of the positive side of many worlds interpretation. So it's not just a better interpretation of quantum mechanics. It really does help us, I think, maybe, hopefully, with some long-standing puzzles in physics. And the reason why it can is because it shifts our attitude on how we do quantum mechanics, okay? So even though we're highly trained physicists, and we know that nature is truly quantum mechanical at heart, almost always, when we write down a quantum mechanical theory, we start with some classical theory, like a simple harmonic oscillator or electromagnetism or what have you, general relativity, and we quantize it. We're all taught a set of rules for turning a classical theory into a quantum theory, okay? But presumably nature doesn't do that. Presumably nature just is quantum from the start, and the puzzle is how you go from the quantum world to the classical world, not the other way around, okay? So what I want to suggest is that maybe this attitude of throwing away our classical preconceptions and thinking about quantum mechanics first might allow features of the observed world to emerge in a natural way. And the biggest question we can ask is about quantum gravity, right? Gravity exists. Here's Albert Einstein when he was young and inventing the general theory of relativity. And according to general relativity, space-time is curved, and we observe that curvature as gravity, okay? So the rule in general relativity is that energy or mass or whatever, the stuff of the universe, causes space-time to curve. It affects the geometry of space-time. So this motto that I put in the bottom right here, geometry is related to energy. That's the rule of Einstein's theory of general relativity. Now, we don't understand quantum gravity. That's the classical gravity, but we don't understand the quantum version. But then again, we don't even understand quantum mechanics. So here's the idea. You know, we've been very, very successful over the course of the 20th century in quantizing classical theories. The entire standard model of particle physics is a classical set of rules that we then quantize in a very specific way, okay? Maybe our luck has run out. String theory and other approaches to quantum gravity are still classical theories that we try to quantize. But maybe that procedure just doesn't work for gravity. Maybe it's just not appropriate. Or maybe it could work if only we knew what it was we were quantizing, but we don't, okay? So maybe the thing that we can try to do is, rather than quantize gravity, to find gravity within quantum mechanics, to start with a quantum wave function and use ideas like entanglement and entropy and the Schrödinger equation, the Hamiltonian and so forth, to see how quantum space-time can emerge. So I'm not going to talk about this because we've run out of time, but also it gets very technical very quickly. But you can look it up on the internet, and I talk about it in the book. Whoever wins the copy of Something Deeply Hidden will hear me talk about it a little bit. The idea is that we can basically figure out an effective geometry to space-time using quantum entanglement in a central way. So that in this scheme, rather than just saying geometry is related to energy, we say that geometry is related to entanglement, and entanglement is related to energy, and therefore via that relationship, they become related to each other. It's a very young, just started kind of audacious program trying to extract the reality of the real world from the quantum wave function, but I'm optimistic that it's going to go someplace interesting. So for my final slide, I will leave you with this quote from David Deutsch, who is a famous physicist, one of the founders of quantum computers, and a big proponent of the Everett interpretation of quantum mechanics. And Deutsch says, despite the unrivaled empirical success of quantum theory, the very suggestion that it may be literally true as a description of nature is still greeted with cynicism, incomprehension, and even anger. So I hope that some of the words I said today will at least lower the amount of incomprehension. I can't really speak for cynicism and/or anger, but I hope that those go away too. Thank you very much.
Lucas, microfone. Tá.
Tá ouvindo agora?
I can hear you now.
Okay. So thank you very, very much. I'm still processing everything we heard from you, and I'm sure everyone is truly amazed by everything you presented. We just have some questions here. I'm gonna look at the chat. Okay, let's see which was the first. Okay, the first question is from Jefferson. He made it in English, so I don't suppose he needs a translation. He said a translation of your answer. He said, "You said that there are people who believe in hidden variables, but what about Bell's theorem and the EPR paradox? It didn't resolve it?"
That's right. So that's an excellent question. There's a misunderstanding in many quarters that Bell's theorem ruled out hidden variables. What Bell's theorem actually ruled out were local hidden variables, which means a theory where not only does everything exist individually at different locations in space, but all the interactions and all the influences between them are purely local, okay? But no one ever really proposed a local theory of hidden variables. People wanted them, like Einstein and others, Schrodinger, would have liked to see such a theory, but no one ever proposed one. Bell's theorem explained why, because they're impossible to fit the data. There are nevertheless theories of hidden variables that have non-local dynamics in them. So that's what Bohmian mechanics actually does. There are particles that have locations in space, but they are influenced by what other particles are doing in a non-local way via the wave function. So that's completely compatible with Bell's theorem. In fact, it was Bell's favorite interpretation of quantum mechanics. John Bell thought that Bohmian mechanics was very promising. He was not a big fan of Everettian quantum mechanics.
Okay, thank you for the answer. We have another question. Rafael Souza, if you want to turn on your microphone, you can make the question.
Vocês estão ouvindo?
Sim.
Okay. First of all, I'm very nervous, so I hope you use the correct words. But first of all, I want to say thank you very much for being here with us today. It's very important to me because I love physics and I love science. And my question is, how could we bring the concepts of quantum mechanics close to people? Because here in Brazil, science, physics is seen as a difficult subject matter and full of calculations and etc. So I want to know by you, how could we bring these concepts close to us and make people like more the science, the physics, and the quantum mechanics? Thank you very much.
Sure. I mean, I think that's also a great question because, you know, science is something which I think everyone should enjoy and appreciate. You know, not everyone can be a professional scientist. That's fine. Not everyone can be a professional football player either, but we can still enjoy it, right? And so I think that I would like it if everyone could appreciate what science has to say, up to and including quantum mechanics. And I think that, you know, there's no secrets to doing that, honestly. I think it's a matter of being enthusiastic and passionate about it and doing the work to make your ideas as accessible as they can be. So that's both spreading them through, I don't know, the internet and books and talks and whatever, but also making them understandable. And I think that in the case of quantum mechanics, there's a special challenge because quantum mechanics is so difficult. It's so hard to understand and so counterintuitive. And like Feynman says, we don't understand it yet. There's a temptation when we talk about quantum mechanics in the popular sphere to just say, wow, it's really bizarre, it's spooky, we'll never understand it. And I think that's a mistake. I think that's the mistake that we make, to pretend that quantum mechanics is somehow impossible to understand even for physicists. Whereas what I like to do, I admit that quantum mechanics is hard, but it's completely understandable to physicists and to anyone else if they really try. And I think that just making that clear, that it's just physics. It's not mystery. It's not mysticism. It's hard because it's far away removed from our everyday world. But if you put your brain to it and you know, read books and watch YouTube videos, etc., anyone can understand quantum mechanics.
Okay, thank you for your answer. We have one more question from Professor Bertulio. He's a professor here in the Department of Physics.
Hello, is everybody hearing me?
Yes.
Yeah.
Okay. First of all, I'd like to say that this is a gift and an honor to receive you, Professor Carroll, today in our university, even remotely, but this is a great thing for our students and to us professors, teachers as well. So thank you very much for your generosity. My question is, if Born's rule, which is postulate in the Copenhagen interpretation, if this probabilistic feature is also natural in the many words interpretation, or if you have to put it by hand or as a postulate as well.
Good. That's a crucially important question. In fact, if you go to meetings on the foundations of quantum mechanics, discussions of the many worlds interpretation are largely devoted to discussions of the Born rule and how you can derive it. Supporters, such as myself, say you don't need to postulate the Born rule in Everettian quantum mechanics. You can derive it. But not everyone agrees, and it's tricky. So here's the thing everyone agrees on. If you're going to derive something, if you're going to use the mechanism of quantum mechanics, the formalism, the apparatus, etc., it's going to be that the probability is the wave function squared. It's not, there's no chance it's going to be the probability is the wave function cubed or the logarithm or anything like that. The wave function squared is the set of numbers between 0 and 1 that are conserved over time. Okay, it's a very natural probability measure. But there are questions about whether or not we should call that a probability at all. The idea being that in Everettian quantum mechanics, the wave function evolves completely deterministically. There's no random jumps in Everett. What there are these splittings, but you cannot even ask, well, which branch am I going to end up on? There will be a version of you on each branch, even though there's slightly different versions of you. So the attitude that I have is that, remember, decoherence happens very quickly. So the branching of the wave function happens very, very quickly, far faster than any human being could ever comprehend. So the universe branches, and there are now 2 copies of you, okay? And neither copy knows which branch they're on. So even if you know everything there is to know about the universe, if you know the wave function of the universe entirely, there's still something you don't know, namely which branch of the wave function you're on. It's just like not knowing when a certain volcano is going to erupt or a solar flare is going to go off, okay? What we do in those cases are assign uncertainties. We assign a probability that a volcano is going to explode or a solar flare is going to go off. And in the case of Everettian quantum mechanics, the right probability to assign is just given to us by the theory. It's the wave function squared. So I think it makes perfect sense. I think there's no room to add an extra postulate for probability, but I think there's also no need to either. It's a different thing than we're used to, so it takes some getting used to, but I think it all fits together nicely.
Thank you so much.
Okay, let's go to one more question from João Marcos. He's saying, the many worlds interpretation predicted the behavior of the wave function in the Everett interpretation can't be observed because, as you had said, the wave function becomes independent or orthogonal. So can we still call it science, or is it just a mathematical solution of the wave function, like the white holes for Einstein field equations?
Well, I think it's different. You know, I think that this is unlike a white hole for Einstein's field equations. The branching of the wave function is something that is predicted to be happening all around us right now. Okay, from the initial conditions that we have. You know, again, there is a prediction in many worlds that is not testable, namely that there's another world, okay? But there are predictions that are testable, namely the wave function always obeys the Schrodinger equation. So there are experiments going on right now because in other theories of quantum mechanics, like the collapse theories that I mentioned, the wave function does not always obey the Schrodinger equation. It dynamically and randomly collapses. So if you do an experiment that finds evidence that wave functions are dynamically collapsing, like Roger Penrose has such a theory, right? These are testable. And if one of them turns out to be right, then the many worlds interpretation will be wrong. It will be falsified. You don't need to be able to see the other worlds. Now, you can ask yourself, well, if I can't see them, should I care about them? And I think the answer there is, if you don't want to care about them, that's fine. But if you want to deny that they're there, you need to come up with an alternative theory. And Everett is the simplest theory. It's just the wave function in the Schrodinger equation, right? There's no reason to deny that they're there. If they make you uncomfortable, if they bother you, those are not good reasons to deny their existence.
Okay, thank you. And well, we have one from Carlos. So Carlos, you can speak now.
Professor Carroll, first thing, was a great lecture. So thank you very much for your presence, for your talk. So we really appreciate it. And I have a question, talking about terms of energy, for example, in the branching of the wave function, does it have a preference direction? For example, we live in a universe where entropy tends to grow over time. So was the preferred direction that the wave function choose to go in our universe, say like that?
Yeah, no, that's a very good question also. These are all great questions. Clearly, you've been paying attention. I like to hear it. There is a direction in the real world. I would say, in my view, the directionality of time in the many worlds interpretation has exactly the same character as the directionality of time in statistical mechanics, okay? In statistical mechanics, we say, look, you have underlying laws of physics where particles bump into each other. The laws of physics have no direction of time. They're perfectly reversible. You can run them either way. But in the real world, there's a direction. Entropy increases. And the reason why is because there is a boundary condition in the past. We started in the universe with very, very low entropy. It's exactly the same story for quantum mechanics. The fundamental equation is the Schrodinger equation. It has no directionality of time built in. It runs equally well forward and backward. But we have a boundary condition in the past. There were very few branches, okay? There was essentially one big branch of the universe, and it's been splitting ever since. Now, why is there a boundary condition in the past? In either case, we don't know. That's a good question for cosmology. Some of us have ideas and proposals, but we don't know what the final answer is. That's part of the ongoing research program. I mean, that's what I like to emphasize, is that Everettian quantum mechanics is nowhere near completely understood. We have a lot of work to do to map it on to the reality we observe.
Thank you for your response, and I think that makes it the field more interesting. There are so many things you know and research. So thank you very much again.
Sure.
Okay, thank you. One more question. Now, Professor Carlos Romero, he's also a professor from the physics department here.
Thanks for your nice talk. It was really clarifying for me. Particularly, I think I was one of the people who had some misconceptions about Everett interpretation. Now, when I think of the wave function of the universe, immediately it reminds me of a proposal called quantum cosmology. And in the context of the interpretation by Everett, and also the procedure of quantizing the geometry of the gravitational field, what do you think of this? The perspectives they have on this line of research?
Yeah, no, I mean, it's absolutely true that quantum cosmology is an important subject where Stephen Hawking and James Hartle, in their foundational paper in, I guess, 1980 or 81, maybe 81, they called it the wave function of the universe. That was literally the title of their paper. And it means the same thing, but with a slightly different orientation, because in cosmology, I know this, I can say this as a long-standing cosmologist, we simplify everything, right? Like the universe is much simpler than the Earth is because the universe is more or less smooth everywhere. So most people in the context of quantum cosmology, when they say the wave function of the universe, they mean the wave function of the very small number of degrees of freedom that describe the universe on largest scales. That is slightly different than the sense in which I was using it to mean literally the wave function of everything in the universe as well as the universe itself. And in fact, if you look at Hugh Everett and his thesis in 1957, when it was eventually published, the title was The Relative State Formulation of Quantum Mechanics. But his first version was called The Theory of the Universal Wave Function, because what he was really emphasizing was that the observer has a wave function also, not just the thing being observed.
Okay. Oh, thank you very much. Thank you.
Okay, apparently we have one more question. Regiane is asking, how is it testable? I think maybe she's speaking about like how could you experimentally define whether Copenhagen or the many worlds interpretation, which is correct?
Right. So I think that, you know, there are two separate questions. How can you test many worlds, and how do you test it against Copenhagen? So testing many worlds, I think I've already talked about. Like, we could rule it out tomorrow if we just found an experiment where a wave function didn't obey the Schrodinger equation. And that's something people are looking for. If you have the way that, just to fill in the details a little bit there, in these theories where there are spontaneous collapses, generally energy is not conserved in these theories. This collapse process injects energy into the system. So what you can imagine doing is making a very, very, very cold condensate, like a Bose-Einstein condensate of atoms, and just let it sit there. And according to the Everett interpretation, it should just sit there forever. According to the spontaneous collapse system interpretations, it should spontaneously heat up and stop being a superfluid. So that's going on. That is something that could easily happen. That's not in comparison with the Copenhagen interpretation. And the reason why is because the Copenhagen interpretation is not just well defined. It's not Everett's fault. Everett interpretation is perfectly rigorously defined. Here are the equations, here are the system states. Whereas the Copenhagen interpretation has vague, undefined terms in it, like observers and measurement, and they'll never pin down exactly when that is. So it's just impossible to compare the two, but it's not because they're not trying, it's because it's not a fair fight.
Okay, thank you. Well, we don't have any other questions in the chat, so I would like to make a question, and I believe that would be the final one. So when I was reading Everett's paper, I saw that one thing that he was very strong about is one of the things you talked in the end on the formulation of a quantum mechanical interpretation which could help in the task of quantizing gravity. And one of the things he talks about like, well, if space is closed, like it was one of the possibilities back then, cosmologically, then there's no point in talking about an external observer and so on, and then Copenhagen interpretation wouldn't make sense when applied to the whole universe. But today, with the discoveries we've made with like dark energy and so on, and the expanding universe, we don't think that the universe is closed anymore, right? And so do you think that would have an impact on his theory in any way? Like, would it lose something by not following that original logic that Everett used when to apply it for cosmology?
I think what's happening here is that there are two different definitions of the word closed that are relevant here. Cosmologists often talk about the universe being closed as in spatially finite, or open or flat, right? The geometry of the universe on very large scales. And like you say, the data that we have now are compatible with a universe that is either flat or open, that goes on infinitely. But there's another use of the word closed, which is in thermodynamics or quantum mechanics, where a closed system is just one that doesn't interact with anything outside. Whether or not it's spatially infinite, it can still be closed, okay? And that's the sense that is relevant to Everett's interpretation of quantum mechanics. It's an interesting historical fact that he invented the many worlds interpretation because he was thinking about quantum gravity, okay? As a graduate student in the 1950s, he was one of the first to take seriously, how do we quantize gravity? And he realized that this idea that was common in Copenhagen interpretation, that you stand outside the system and look at it, wouldn't make sense if the system was the universe. And that's just as true if the universe is spatially finite or spatially infinite. So the cosmological discoveries about the geometry of the universe don't really affect our credence in the Everett interpretation one way or the other.
Okay, now it makes more sense. Thank you. Okay, so, well, by the time I think one more person made a question in the chat, due to the time, we're going to make that one the last one. Okay. Thank you for everyone who participated. Rafaelis made the following question. She said, I have another one. Okay, another question. Do you agree with the Hawking's thought about that the Earth shouldn't be our first choose, but that we would explore and maybe colonize the solar system? Don't.
Well, I think that I get what he means, what he meant, Stephen Hawking. Life is fragile, and as recent events have indicated, we're not always good at taking care of our own planet. And, it's as Elon Musk likes to say, we would like a backup for the biosphere, just like you should back up your computer. There are disasters that happen, no matter how careful you are. Life only exists on one planet, as far as we know, and spreading it widely through the universe would make it much more likely for life to survive for a very long time. I do believe that that's a very good idea. It's not a short-term project. It's not cheap. It's not easy. I suspect strongly that the first people to go to Mars will not come back. It's just too hard to build a round-trip mission. It's going to be a one-way mission to Mars. And so that's a daunting prospect. But yes, I think we should look into it. I think we should recognize the dangers and the difficulties and the expense, but we should take it seriously as a future prospect.
Okay, so thank you very, very much for your participation, for your lecture, for answering our questions very patiently. We are truly honored to have you here, and well, that's it. But thank you very much. My
pleasure. Thanks for having me on, and thanks to everyone for coming.
Yeah, thank you very much. We're probably gonna, if the guys confirm me now, we're gonna announce the winner of the book. So feel free if you want to join us for that. Feel free. If you can't, it's okay as well. But we just thank you.
I got to run away. I have another thing coming up, but okay. I wish everyone luck, and I hope that everyone who doesn't win the book buys it. It's a good book. You should read it.
Okay, I'll certainly buy it. I am not in the list as a possible winner because we are in the organization.
Right, that's fair. Yeah.
Yeah. So to be fair, but for sure I'm gonna buy it after it. Thank you very much.
Thanks. I appreciate everyone coming. Thanks for having me. Bye-bye.
Bye, Professor. Bye. Thank you. Well.
E aí, pessoal?
Saiu on.
Ai, meu coração.
Eu já posso gritar?
Já saiu.
Tô batendo palma aqui, tô meio em choque. Eu não sei, mas a gente tava se tremendo um pouco, todo mundo falando ali no grupo. Tá todo mundo meio, calma, vamos falar tal coisa, vamos fazer tal coisa. Por quê?
Poxa, nem deu pra fazer minha pergunta de matriz de densidade, papai entrou. Droga.
Meu amigo, quando alguém mandou muita molesta, Raishan Carroll, eu caí da cadeira.
Aquele eita moleque, meu amigo.
Eu estou anestesiada até agora.
Mas assim, a gente vê vídeo na internet. A gente vê vídeo na internet do bicho apresentando e tal, mas tipo, ao vivo é outra coisa. Tipo, é genial como ele explica as outras coisas. Tem um momento que tu para e fica, caralho, olha só o que ele tá fazendo ali. Olha só ele botando o operador com a carinha de boy e tal, e introduzindo voluntariamente o operador desse jeito. Eu fiquei, meu amigo.
Exatamente.
Brabo, ele botando os gatinhos ali.
Ele não quis matar a sessão espírita no Tabuleiro Ouija para trazer de volta a Carl Sagan para dar uma entrevista aqui pra gente. Tá bom.
Eu ia falar isso agora, só que eu ia sugerir, sei lá, Hawkins, Einstein. A gente chama o rolê todo.
Chama tudinho.
Galera,
manda no zap deles, manda no zap.
E aí a gente resolve.
Galera,
Agora vamos levar a sério só o final aqui, porque tem gente esperando por alguma coisa, né, velho?
Isso, exatamente.
Pois é.
Então,
Vamos
galera,
calmar, voltar ao decoro.
Tem a última surpresa ainda, pô.
Volta ao decoro.
Então,
Fazer
galera,
o sorteio e a última surpresa.
Passou.
Então, galera, só alguns comentários, né? A gente queria primeiro pedir, né, para vocês ficarem aí um pouquinho mais, como já foi falado. Teve gente, acho que até na emoção acabou saindo, achando que tinha acabado. Mas agora a gente vai ter uma breve cerimônia de encerramento, né, só para fazer os devidos agradecimentos. Também fazer o sorteio do livro, né, passar algumas coisas para vocês. Tá bom? Então a gente pede que vocês fiquem aqui com a gente, só mais aí uns 30 minutinhos. E aí vamos estar livres aí para pensar em tudo que aprendemos, né? Para quem é mais novo, para digerir, para quem é mais novo no curso aí, pensar como essas coisas afetam aí o que é que você vai escolher como projeto
livro
no futuro, etc.
Sorteio.
Né? Muito bem, galera. Então, assim, eu acho que quem vai conduzir daqui para frente é a Michele, né? Então,
Sou eu, macho.
Quem?
Sou eu que vou fazer o sorteio, macho.
Ele vai fazer o sorteio, isso.
O sorteio vai ser logo agora?
Ou vai ser a surpresinha?
Eu achava que ia ser ao contrário.
Vamos deixar a surpresa.
Bonito.
Vamos fazer uma surpresinha aqui rapidinho?
Vamos fazer a surpresa primeiro, mas só antes de eu terminar a minha fala. Antes de eu terminar a minha fala e passar para a Michelle, eu só queria realmente agradecer aí a galera do Cafis inteira que batalhou bastante aí para o evento dar certo, né? Esse pessoal é muito bom. Eu não tenho trabalho, não faço nada, eu só fico olhando eles fazerem. Porque é uma galera extremamente competente, assim. Era uma das propostas, né, que a gente tinha quando iniciou o Cafis, a chapa, né? É que a gente tivesse boas pessoas para que o trabalho não fosse muito para ninguém específico, né? E todos têm cumprido esse trabalho, né? Não somos talvez os melhores, os mais incríveis, mas temos nos esforçado para fazer um bom trabalho e eu espero que vocês estejam aproveitando, né? Agradecer para os que estão fora das câmeras, né? Nosso querido Emanuel aqui, que estava nos dando todo o suporte tecnológico. Ele está escondido, vocês não veem, né? Alguns ouviram ele falando aí as histórias no começo desse período da tarde, mas nos deu uma grande força aí. Os professores, em geral, que aceitaram o nosso convite de estar presente, né? Outros professores que não estiveram presentes, porque a gente não tinha espaço para todo mundo, mas que prestigiaram, assistindo as palestras, comentando, compartilhando, incentivando os estudantes a participarem, os estudantes deles. Então, a gente é muito grato por todos, em geral, que participaram, e tem um agradecimento especial aí que eu vou passar para a Michelle aí, e ela vai conduzir a partir de agora.
Então, pessoal, organizar um evento assim é cansativo, demanda muito planejamento. Tá dentro do curso de Física, demanda uma certa persistência, a gente sabe que não é algo muito trivial, mas eu tô mais nervosa agora do que quando eu estava falando com o Sean Carroll, porque essa é uma pessoa muito especial e nós resolvemos fazer uma homenagem a essa pessoa, porque acreditem quando eu digo que não teria departamento de Física sem essa pessoa mais. Então, nós resolvemos fazer um pequeno agradecimento para Dona Nazaré. Vou aqui, para quem não conhece a Dona Nazaré, ela é a dona da Física. É assim que a gente fala. Vocês já falaram com a dona da Física? E todo mundo já sabe que a gente está falando de Dona Nazaré. Ela está sempre ajudando a gente nas reuniões de departamento, está sempre ajudando a gente para saber o que está acontecendo com as cadeiras, quando os alunos vêm falar com a gente, quando a gente quer fazer um evento desse tipo, precisando de uma turma, precisando de uma sala vazia para a gente poder fazer alguma coisa, tudo, a gente corre para os pés de Dona Nazaré. Eu até hoje não sei como ela ainda aguenta a gente, porque principalmente é muito complicado aguentar Cláudio. E ela é uma lady perto dele, só ela consegue fazer isso. Então, vai ser um pequeno agradecimento para uma pessoa muito importante, uma pessoa essencial, como eu falei, e no momento que o curso de Física estava um pouco apagado e algumas coisas estavam acontecendo dentro do departamento em si, ela estava ali no meio, fazendo tudo. Então, deixa eu só compartilhar aqui a minha... Eu ia colocar uma fotinha aqui dela para vocês saberem, mas eu não estou conseguindo apresentar, eu vou abrir pelo WhatsApp.
E o período online também, né? Aquela famosa reunião antes do período suplementar, todo mundo estava na correria.
Vocês estão conseguindo ver? Vamos lá.
Agora foi a apresentação.
Estou sim.
Tá dando para ver a foto dela, Lucas?
Tá vendo, vamos ver.
Tá sim.
Agora voltou já.
Então vamos lá, eu escrevi um negocinho aqui. Hoje resolvemos homenagear uma pessoa mais do que especial. Dona Nazaré é a nossa verdadeira dona. É a nossa pilastra do departamento. Sem ela, qualquer coisa cai. Sem ela, nada seria feito. Pode acreditar, ela é a dona da Física. Ela cuida de tudo e de todos e é a mãe do curso. E nós, como filhos, estamos aqui para agradecer. Agradecer por tudo, pela confiança no CAFIS, pela consideração, por toda a ajuda na organização, por cuidar do curso que nós amamos e ajudar a colocar ele para frente. Às vezes, acabamos esquecendo que as coisas não se fazem sozinhas e que tem pessoas por trás de tudo isso. E pode acreditar, se a nossa dona não estivesse por aqui, por trás de tudo isso, nada disso estaria acontecendo. Os problemas que tivemos durante todos os anos, com cadeiras, problemas que os alunos tiveram que passar, tudo foi ela. É fácil esquecer isso quando está tudo prontinho em nossas mãos, mas sempre tem alguém responsável por isso. Então, não esqueçam das pessoas que fazem tudo isso. E, principalmente, não esqueçam da Dona Nazaré. Obrigada, Dona Nazaré.
E aí, obrigada a vocês, gente. Obrigada a vocês. Eu sou funcionária, eu só trabalho ali por causa de vocês, é para servir a vocês. Eu não faço nada obrigada, nem nada. Simplesmente eu tento resolver, mas muitas vezes vocês me perdoem que eu não posso fazer nada, porque, enfim, a máquina funciona de maneira diferente. Mas o que tiver sempre ao meu alcance, vocês vão ter sim, porque vocês são alunos brilhantes, eu sei que para fazer física não é fácil, e vocês são alunos brilhantes, eu vi agora vocês falando inglês aí, fluentemente, vocês são maravilhosos, então a gente tem que fazer alguma coisa assim, sabe? A gente não pode ficar de braço cruzado, não. É por isso que eu sou conhecida também como briguenta, sabe? Assim, que vou à luta, porque eu aprendi a brigar pelo meu departamento, pelo departamento que eu defendo, pela minha instituição, entendeu? Não faço nada forçado, eu faço de coração mesmo, de amor mesmo, porque eu amo todos ali. Ali é minha família. Eu estou passando por maus lençóis, porque não estou indo para a universidade, estou doente, sabe? Estou com problema sério, tive dengue, tudo. Estou aqui muito ruim dos ossos mesmo, sabe? Sem poder pegar nas coisas, tudinho. Mas eu estou com muita saudade de vocês, viu? E você guarda essa cartinha aí, porque aí eu quero guardar, quero colocar ela num lugar especial, tá certo? Mas vocês moram no meu coração, tá bom? Viu? O que vocês precisarem depender de mim, eu estou lá. Não sei quanto tempo mais, porque eu estou muito caidinha mesmo, sabe? Mas quando eu estiver lá, porque o Gustavo é excelente, o funcionário agora, viu? Também é como eu, vai à luta, sabe? E consegue tudo. O Gustavo é maravilhoso, esse funcionário novo. Então, enquanto eu estiver lá, vocês terão meu apoio, meu abraço, meu aconchego, tá bom? Viu? Muito obrigada pela homenagem, muito obrigada mesmo, viu? Estou com muita saudade de vocês, tá?
Agora quem vai chorar sou eu.
Desmontar os microfones, bater palma. Liga
Vamos
as
salva de
câmeras se
palmas pra
quiser.
Mas vocês são ótimos, foi ótimo o evento. Tá. Vamos ver. Viu?
Eu vou passar
Tchau.
Parabéns, dona Nazaré. Obrigado, dona Nazaré.
Obrigada, parabéns a vocês, são brilhantes aí,
Obrigado,
novos aí,
por
com a
tudo.
carreira linda pela frente. Tchau.
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 Obrigado por tudo.
Beijão aí pra todos. Tchau. Tchau. Tchau.
Vai chorar sou eu. Ah, foda.
Eu tô muito emocionada, gente. Mas
Minha
vamos lá, vamos dar
gente.
continuidade a isso.
Minha gente, com que estrutura que eu vou fazer esse sorteio agora depois? Eu não tenho mais.
Adeus.
Enquanto o pessoal se recupera, deixa eu dar mais alguns poucos avisos. Eu sei que vocês já estão cansados de tantos avisos, mas só dois avisos, na verdade, né, enquanto uma cliente se organiza. O primeiro é que, para o ganhador do sorteio hoje, galera, como a gente falou, algumas pessoas de outros estados se inscreveram na Semana da Física. Não sei se estão aqui presentes, tá bom? Para essas pessoas vai haver o fretezinho lá, tudo certo. Para as pessoas que moram aqui, em João Pessoa, na Grande João Pessoa, Cabedelo, Santa Rita, por aí ainda dá para ir, a gente provavelmente vai fazer a entrega pessoalmente, né? 2 ou 3 pessoas do Cafis devem ir devidamente aumentadas fazer a entrega, tá bom? No caso, se o ganhador for aqui e a entrega for presencial, o prazo é até o fim do mês, tá bom? Para chegar o livro para vocês. Se a entrega for por frete, aí vai depender de onde a pessoa mora, essas coisas aí que vocês já entendem, né? Tudo bem? Mas só para deixar claro que eu sei que quem ganhar vai querer saber isso. Então, se você ganhou de João Pessoa, o livro chega até o fim do mês, tá certo? A gente vai entrar em contato, né, no privado, ver direitinho os detalhes, endereço e tal. E se você for de fora, aí vai depender da questão dos correios, tá bom? E a segunda coisa que eu queria dizer era que, como todo mundo sabe, né, estamos aqui falando com alunos, quase todos, eu creio, do curso de Física, ou, enfim, que são membros do CAFIS, né, por definição. A gente estava conversando sobre isso ontem, né, que o CAFIS não são 8 ou 9 pessoas que fazem parte da coordenação, mas são todos os estudantes de Física da UFPB. Então, assim, os estudantes de Física da UFPB, um dos pontos, né, do nosso estatuto é a transparência com os recursos, tá bom? A gente não trouxe planilhas para cá, tal, para não estragar o momento, mas, assim, se qualquer um de vocês tiver qualquer dúvida, interesse de saber como foram alocados os recursos que foram recolhidos aí com as inscrições, podem entrar em contato com o CAFIS, com qualquer membro do CAFIS, né, com os membros da gestão do CAFIS, que a gente vai divulgar isso com toda a transparência, tá bom? Então, isso aí, né, a gente não tem nada para esconder nesse respeito, tá certo? Então, quem tiver interesse pode entrar em contato que a gente manda para você no privado aí a relação de como esses valores, onde é que eles estão, o que é que foi feito, tá bom? Então, só essas duas coisas que eu queria dizer e aí passar o tempo aí para a McLean agora.
Acho que deu para recuperar um pouco o fôlego até o momento. Acho. Então, pessoal, como dito anteriormente, a gente vai ter o sorteio do livro do ilustríssimo Shankar, que vai ser o do Something Deep Hidden. O inglês hoje tá excelente. Mas a questão vai ser justamente desse livro. Eu estava mostrando sem colocar a apresentação. Eu sou um gênio. Mostra aí, Carlos. Que tu tem um livro. Mas imagem meramente ilustrativa, porque esse é o livro dele. Deixa eu pegar outra que tá chegando para vocês. Cara, calma aí.
O de vocês vai ser novo. Esse aqui eu tenho já.
Isso aí já é o encosto da porta dele.
É demais. A capa é muito bonita, tem até uma capinha que separa e tal, tem uma folhinha na frente, é de capa dura aqui, ó. Separa, fica só o livro de tecido, ó. Aqui com o nome aqui gravado, ó.
Tudo de bom.
E a
como Michelle é a blogueirinha da gestão, Michelle ia fazer um unboxing com vocês aqui, tá entendendo? Mas teve um probleminha com a Amazon, em vez de...
O homem bonito aqui, ó, o homem bonito.
em vez de entregar ontem, eles só vão poder entregar com mais uma semana. Então, só vai estar chegando pra gente na quinta-feira que vem, tá certo? Por isso que a gente pediu esse prazo aí até o fim do mês para poder entregar o ganhador. Mas aí é bom também que, como a gente não vai fazer um unboxing, quem ganhar vai ter o prazer, né, de abrir, sentir aquele cheiro de livro novo. Então, vai direto na caixa.
E aí é bom, viu?
Estão perguntando quanto foi. Foi R$156.
Essa é a média de preço. Porque
A
não
cara do
tem.
Daniel ali foi maravilhosa escutando isso aqui agora.
É porque ainda tem. É como lançou agora, só tem capa dura em inglês, né? Não tem nem capa de normal, nem português. É recente, é muito recente o livro aí, enfim.
Mas assim, pessoal, é Semana da Física, né? Eu acho que é mais do que merecido, né?
Pois é.
A gente
Depois
não
de
dá
uma dessa.
reais, né? Também tem que ser uma coisa bonitinha para
Pois é.
representar.
Para marcar.
Bom, vou colocar para transmitir a tela aqui, para ninguém dizer que eu estou roubando. Vou mostrar aqui que tem meu nome aqui nos 104 participantes. Qualquer jeito eu ganho. Colocar aqui.
Tartar está dizendo que se roubar, roube para ele.
Deixa eu ver aqui. Calma aí que o negócio aqui é...
Era para ter falado pro Sean Carroll escolher um nome que nem a Semana da Física do ano passado. Ainda não. Tá carregando. Vai aparecer agora. Pronto.
Tá com 300 coisas aqui, das palestras anteriores.
McLean, só para lembrar todo mundo, né, que nenhum dos membros do Café está na lista, tá certo?
Tá na lista, exatamente.
Infelizmente.
Bom, mas vamos tentar aqui fazer um sorteio que a gente aqui... Pegamos o quê? Sorteador de Instagram mesmo. Calma aí que eu tava... O gênio aqui já tinha sorteado um número aleatório. Só para testar. Desculpa você que é o número 85, mas infelizmente não foi dessa vez. Colocar aqui ativo. Dá para ver o que eu tô fazendo na tela?
Dá para ver. McLean, só para explicar, né? A gente tem uma planilha com o nome de todo mundo que é inscrito, né? A planilha tá
sim. Aqui, ó. Tá aqui, ó. O nome de todos vocês.
Tá por ordem alfabética de 1 a 104.
Ordem alfabética.
De 1 a 104.
1 a 104. Tá aqui, ó. Não dá para ver ali embaixo, mas tá ali. E aí, todo mundo pronto? Eu tava tentando procurar algum negócio de rufar tambor, mas não achei.
Vai aqui, ó.
Boa, muito obrigado. Coloquei até a animação, bora. 3, 2, 1 e... Agora quem molesta é o 51.
51.
51. Tá.
É uma boa pedida.
Tá indo.
Tá. Para... Joshua. Tá aqui?
Acho que ele tá aqui.
Tá na live.
Parabéns.
Tá na live? Moleque.
Tá na live, fala aí.
Boa, bem demais.
Tá escutando? Alô?
Tá.
Tudo ok.
Eu vou pegar aqui o compartilhamento, pera aí.
Mostra o livro aí de novo que ele vai levar, Carlos. Vamos fazer bem...
Aqui, ó.
Fazer bem programa da Polishop.
Bem show do milhão.
Só ligar a luz aqui.
O engraçado é a galera tudo começando a sair depois que já viu que não ia ganhar.
Exatamente. 81.
Aqui, ó.
Um livro do Sean Carroll que vale mais que dinheiro.
Ainda conversou com o Sean Carroll ainda, ó.
Se eu tivesse colocado meu nome dentro, eu ainda não ia ganhar. Se fosse só 104 nomes mesmo, assim, um atrás do outro, eu ainda não ia ganhar. O único sorteio que eu ganhei na minha vida todinha foram 2 pirulitos. Eu não tô nem brincando. Um era de manga, um era de limão. Eu não queria o de limão, a minha irmã ainda ficou com o de manga. Eu fiquei puta.
Então, galera, parabéns, Joshua, pelo livro. A gente vai entrar em contato contigo no privado para pegar as informações, beleza? Contato. Beleza. Sim, deixa um contato. Não sei se um de nós temos, né? O contato dele. Então
eu tenho.
Pronto, beleza. A gente entra em contato para ver os detalhes direitinho. E aí eu acho que vai um prêmio bem válido, né? Vai poder ir lembrar.
Esse aí não vai dizer que não valeu a pena ter se inscrito na Semana da Física.
Eu nunca ganhei sorteio também, porque até...
Se alguém dizer que não valeu a pena se inscrever na Semana da Física, eu mesmo faço favor de ir até a casa da pessoa e arregaçar ela.
Epa. Tá vendo aí? Na frente de Martinha não fala tanta coisa.
Mas, galera, Muito obrigado pela participação de todo mundo. Vamos deixar vocês irem para descansar e pensar no que aconteceu. O pessoal do Cafis quer mandar um salve aí, dizer mais alguma coisa antes da gente encerrar oficialmente?
Bem, eu quero agradecer
a vocês,
Olha aí.
principalmente. Vou falar, Carlos, tá interrompendo. Vai.
Não, fale aí.
Não, agora você vai falar, se lasca.
Eu queria agradecer pela cooperação de todos aqui, em primeiro lugar, porque sem a equipe a gente não teria feito nada, tanto programação, tanto transmissão, tanto as reuniões decidindo, enfim, queria agradecer a todos vocês, porque, enfim, fazendo tudo em conjunto, o trabalho fica mais leve. E também a todas as pessoas que tiraram esses 2 dias para acompanhar a gente, para participar desse evento tão bonito e que, com sorte, ano que vem, presencial, melhor ainda, e enfim, a gente não vai parar por aí.
Aí, vai, McLean, fala.
Não, eu não tenho mais nada pra dizer, não. Depois de uma fala dessa, tá doido?
Então, eu vou falar. Pessoal, eu queria agradecer, obviamente, a presença de todos vocês. Esse evento foi criado para vocês, para o curso de Física estar se destacando, que era uma coisa que estava meio apagado. Estava apagado aí no meio dos outros. E nós somos apaixonados, sabe? O povo do Cafis é um bando de louco apaixonado pela física, essa é a nossa definição. A gente não ganha nada em troca em relação a isso. Não é uma coisa remunerada, nem extremamente prestigiada. É cansaço e, para não dizer que só tem, tipo, o lado negativo, a gente tem esses momentos. E eu queria agradecer principalmente aos meus amigos do Cafis, porque trabalhar fazendo o que gosta não tem preço, acreditem. Pode ser uma coisa muito cansativa, mas no final sempre tem a animação, o prestígio de estar trabalhando, fazendo a coisa que você gosta com as pessoas que você gosta. Não tem uma reunião que a gente faça da gestão que a gente não termine em gargalhadas, resolvendo os problemas, mudando tudo, no meio assim, gargalhadas, sempre. Então, é um prazer, eles são muito minha base dentro do curso, são as pessoas pelas quais eu admiro muito, estou sempre me inspirando neles, e são, além de colegas de curso, colegas de centro acadêmico, de tudo ali, eles são meus amigos na vida. Então, eu queria agradecer muito por estar com vocês nesse projeto e ter feito tudo isso aqui com vocês. Eles viram ontem no grupo que eu mandei até foto chorando. Meu Deus, eu tô na TPM, que eu tô chorando porque a gente tá fazendo a Semana da Física, que tá muito bom. E Emanuel dizendo que eu era boiola, essas coisas. Mas eu realmente... É um prazer muito grande estar fazendo esse evento com vocês. Eu queria agradecer também por fora por Emanuel, que está aqui enchendo o saco, mas eu vou agradecer do mesmo jeito, que o povo sabe que não tem como desvincular mais imagem Michelle Emanuel, Michelle. A gente tá grudado em tudo, então ele não tá nem no Cafis e ele faz as coisas do Cafis tudo. E ele que luta, porque eu tô aqui na casa dele. Então, obrigada por tudo, até por ceder o espaço e a sua mãe, que ela é maravilhosa e nos atendeu muito bem aqui em casa. Então, é isso, pessoal. Obrigada por ter participado.
Nada.
É isso aí. Alguém mais do Cafis quer dar alguma palavrinha ou podemos encerrar?
Eu só quero agradecer mesmo pra galera, agradecer nós aí, porque nós é pica.
Amor.
Quer dizer novamente.
Eu queria dizer que
ele não é assim.
É pior. Não é assim que é
ano que
pior.
vem tem mais, viu?
É isso aí,
Vai,
galera.
velho.
Ano que vem tem mais. Os grandes eventos não se acabam, né? Entram em recesso. Então, agora eu acho que podemos oficialmente declarar que a Semana da Física entra em recesso e voltaremos aí entre setembro e outubro do ano que vem. Então, nos aguardem.
Pequeno
abraço, galera.
Pequeno prazo para a Semana da Física. Grande prazo para a monarquia do Cafis.
Tchau, galera. Valeu.
Valeu, parabéns, gente.
Valeu, gente. Boa tarde.
Tchau, pessoal.
Obrigado.
Tchauzinho.
Você é maluco.
Monarquia, ditadura.